Welcome to this webinar on how to simulate the field, combining field studies with modeling in the soil sciences. My name is Simon Clark. I am the European Geosciences Union Projects Manager. And for World Soil Day, which is today, the EGU Soil System Sciences Division is hosting a webinar to help soil researchers navigate the gap between modeling and field studies, with talks and discussions from two speakers. Our speakers are Julia Sophia and Marine van der Meij. They'll be introducing themselves. But before we begin those talks, just a couple of housekeeping. This talk is being recorded and it will be uploaded and published to our YouTube channel. That's the EGU YouTube channel later. So look out next week if you want to rewatch the webinar. And there's also a Q&A box at the bottom of the screen. So if you have questions for our speakers, please enter the Q&A box there. We'll get back to questions after both speakers have finished their presentations. But with that, I think we'll start with the presentations proper. Julia, could you start for me?
Okay, so first of all, thank you for having me at this interesting session. I'm actually speaking to you from a conference connected to water management, which is kind of connected to what I'm going to try and discuss today for this workshop. I actually come from the geomorphology modeling world, and with some information on soil science related mostly to infiltration processes and modeling at large scale rather than at field scale. So when I thought about this interesting session, I was actually thinking about a practical application that we had to deal with in my office. So I actually work for a water management board in a small research center, and the main point of the work we do is handling water for irrigation. And I'm telling you this because I just want to give you an idea of the scale we're working on generally. So we manage irrigation for over 100,000 square kilometers of agricultural landscape delivered by an artificial river, which runs for about 50 kilometers. So my scale of analysis, my scale of understanding must be very wide, with the limitation that comes from being that wide. At the same time, we are talking about volumes of water that over 6 months in a year, which is about 400 millions of cubic meters. And just to give you an idea, it's about 900 percolifas stacked together, which are given to agricultural land. But the way water is given, and that's what brings me to the practical application, people have licenses to use this water from a specific purpose. These licenses must consider environmental flows, which are mandated by law. There are policies that prevent water use when the minimum requirements are not met. It means during droughts, there might be water, but we cannot use it. We have to consider the ecological status of the water bodies. Most of all, these licenses and this way of using water does not consider climate change and water availability. And the way licenses are built is they started 30 years ago, and they accounted for the needs of 30 years ago. They don't consider changes in water demand, but what peculiarly is important for us is we never consider changes at the soil level. And there's a lot of things that come into play when soil degradation happens from the perspective of plant growth or water use. And generally this aspect, at least at the large scale, it's never considered from the management point of view. So the overall idea that we are trying to build is to put together field studies where we can actually understand these small-scale changes and put them on a large view so that we can manage large territories. But the most important thing is all of this we're trying to put together people. And by people, I'm talking about those that do use water, those that do live in these fields, and that sometimes forget or don't expect the changes that we might face. So we work at the field level with actual farmers. They own the land, they farm the land, they actually live of whatever the land produce. And we try to put together their practical experience with field studies at the very small scales, from remote sensing with drones to actually lab analysis on soil characteristics, with the idea of involving them and actually showcase for them what is the reality of changes in soil properties. Just to give you an idea, this is just a table of samples of soil taken from our 4 farms. And I know it's just the shades that you can tell the differences, but this is soils from just one plot. So we have to consider thousands of square kilometers, but we end up with the field that has this much variability over a couple of 100 square meters. Of course, this is a peculiar case, but it's the reality most of the areas we serve. Most of all, we want to understand how these shifts in soil properties can impact agricultural production. And we know and we want to model how the yield responds to the availability of water. That depends on the weather, on the crops, but mostly on the soil. And many of these farmers do not have a real knowledge of the characteristic of the soils locally. Of course, they also have different irrigation practices that can impact the growth and also the characteristics of the soils where they work. We have a very extensive land, and you can find soils of, for example, volcanic or limestone in continental climates. And within a few hundred, actually 50 kilometers, you get similar soils, but in a Mediterranean climate settings. We go from inland all the way to continental climates, but on gravy soil, alluvial plains, given by major rivers. And we have soils that are similar, but in a Mediterranean type of climate close to the sea. So understanding the impact of the soils on this production is for us critical. In red here, you can find soils that are by definition more suitable for certain type of crops. In blues and greens, you see actually the distribution of cultivations in our landscape. So when we talk about soy, the reality is that most of this production grows on soil that it's not meant for it. And it's the same for example, animal feedings or for fresh products, such as, for example, potatoes or sugar beets. So the idea is, can we actually understand the impact of these different soils on this production? And one of the things we focus mostly on is soil organic carbon. I put here is the Cinderella of agricultural climate studies, mostly because it's a scale at which we don't think of. When we think about soil organic carbon, we want to work on the field level. When we enlarge the picture in EU soils, really the quality of the soils and organic carbon is not sufficient for plant growth. In my region, which is Veneto, we are actually one of the Italian regions where there's been the most high recorded loss in organic carbon over our territory because of land use change, because of grazing and agricultural activities, because of how the history of the landscape evolved. And if we look about climate scenarios, there are work done over different areas. This is for Germany, that tells us that soil organic carbon will decrease even further. So the idea was, can we actually model and quantify these effects of soil organic carbon decrease on certain agricultural productions, and mostly sugar beets, potatoes, and soy. Today, I'm just going to show you some examples of what we came up with. And we work in one of our farms. So this is actually one of the farmer plots that we actually worked on, and we organized to provide this experiment on soil changes. And this is a research that was done in collaboration with the University of Verona and Professor Zaccone, which had the idea at the field scale, and I tried to enlarge it at large level with modeling. So what they did is, on the field scale, they built cameras, small greenhouses, where they could test the effect of 2 degrees temperature more inside the soil. Now, 2 degrees temperature is what we expect in the most conservative climate scenario. Each camera has been monitored with sensors throughout different seasons, and we can see that we are able to maintain a 2-degree increase in the area underneath the greenhouse as compared to the outside. Within each plot, there have been planted different plants. The same amount of plants is within the camera and outside. And the idea is to test over different seasons what changed within the soils and in terms of production. So we had 2 years of studies over different sugar beet and potatoes that I'm going to show you. But I'm just going to show you what did happen after the first year that we did the testing. So these are the area with the cameras, and these were for potatoes and sugar beet. At the end of the first season, on your left here, you can see the sugar beet outside the 2 degrees Celsius increase. On the right, this is the effect of the 2-degree increase in the soil properties for the sugar beet. Moving on to potatoes, hopefully it shows on the screen. On the left, you see the amount of potatoes that were picked up outside the cameras and the one that were picked up inside the cameras. And mind that this is the same amount of plants. So the 2 degrees changes didn't impact much the size of the production, but definitely the volume of products. So we saw this in the field. We measured the changes in soil properties, and this was the result of about a 1% decrease in soil organic carbon. 1.6 for the sugar beet, and actually 1.2 for the potato. So with this information, the overall idea was, can we model this effect of the decrease in soil organic carbon by an actual model? So we took the measurement of how the climate has changed for us. We're not talking about future projections, but we are just talking about measurement change in the last 10 years. For us, there's about 0.5 degree every 10-year increase in temperature. There's not much change in rainfall, but we have more days with a lot of rainfall and less days with very short events. Overall, for our landscape, we measured, not in the field, but by data, a 0.3% decrease in organic carbon. When we put this information in our model, what our results is that in the red, you can see the current production, and in the blue, I'm sorry for the noise, I'm at the university. In the blue, you can see the production after the changing climate as we measured it by weather stations. So we do see a decrease, about 5% for sugar beet. But if we compare it to our field study, where we actually simulate these changes physically in the landscape, our production results measured, not modeled, showed about a 60% decrease in production. So the red bar is the one for a regular climate outside the greenhouses. The blue one is the production within, with this 2 degrees raised inside the camera. So what we did is, this was 2023, so actually a quite rainy year in the history. So what we did is we took at the regional level how the climate has been projected to change for the 2.6 scenarios. So we do see an increase in spring and summer. However, the resolution of these models at the global scale are not sufficient for us to model anything. You can see here it's a very large pixels. So with this, it's very hard to model what happened at the field scale. it's even worse for rainfall, where we do see changes overall, more rain in spring, less rain in summer. But again, we cannot really model what happens at the field scale with this type of information. So what we did is we simulated 100 possible future years based on these trends and shifts in climate. And we did simulate multiple rainy event and temperature events to get 100 possible 2023 in the future climate. And we added to this information the percentage of soil carbon decrease that we measured through the experiment in the field. We added this information to a weather generator to provide thousands of possible scenarios, only for 1 year. The result is that we can get modeling of how temperature and rainfall could be in our hypothetical 2023 in the future. Once we do this, we can compare our result. This is again the measured one with the 60% decrease in production with the model. And with all this information and the downscale weather information, plus the field sample characteristic on the soils, you can see that we can actually model quite nicely what we measured in the field with our modeling system. So we have, for example, for the sugar beet, we used to have, with the current weather, about 60 to 80%, 80 tons per hectare of production. But with the climate scenarios, we get to 20. And this is consistent with our microclimate simulation created in the field. So this gives us a two-way validation. One, we have a model that can actually extend our findings at the field to a larger scale and to a longer time frame. Two, the idea of building those cameras, those greenhouses, did work in reproducing a possible scenario of the climate, how we should be seeing it in the future. With this information, this was a year where nobody irrigated. So we are water managers and we're interested in seeing, so what happened if we do irrigate, how that would work. So the truth is, when we do irrigate very frequently, our future weather might receive a similar production than the one we see today. The downside of this, however, is that the water use to maintain this type of production will almost double. And this implies a big use of water, a big consumption of water for irrigation. At the same time, the fact that some farmers might think it's not worth anymore to pursue that type of cropping. So what is mostly important about this application at the field study is that we were with the farmers creating this project. So I could have shown them many of this modeling to the left to provide them with a foreseeing of what might happen. But really, every time I do that, they don't really get inspired by these trends, these box plots, these lines that tells about the future. But they did get very inspired and very scared about seeing their own sugar beets or their own potatoes at the end of the season, just by adding these 2 degrees. So I might have been a bit fast, but my whole idea is that, and this is a sentence from Andrea Rinaldo, which won the Nobel Prize for Water, when we want to talk about feasible agriculture, we need to understand how water resources are going to change. And managing water today requires a dialogue among different people, from people to the legal perspective to actual farmers. With the condition we're going to, climate is changing and we must rely on models to forecast the future demands, but we don't have the luxury to wait to see if these models are actually proven right. When we have a possibility of working at the field scale with actual people, with actual characteristics of the land, we can actually give a tangible proof of what's expected and what's waiting for us. Thank you.
Thank you so much, Julia. So we will now move on to our next speaker.
All right. Well, welcome all to this webinar on the World Soil Day. And thank you for the organizers for inviting me as well. My talk will be completely different than the previous one, where you look towards the future using modeling, mainly look backwards in time, you could say. I'm a soil geographer, so I look at soil landscape processes, soil landscape patterns, and how soil development and erosion, landscape development influence each other over time. For this, we use different methods. We often start with field observations. We do different measurements, maybe different dating techniques, and in the end, we try to combine all these insights into numerical models. That's what I will be talking about today as well. So this project is about bioturbation. Wait, let me first share the content of the presentation. So first, start with the motivation of the presentation, talk about the background and what we actually try to achieve with this project. Then talk about luminescence, or OSL. It's a dating technique which we will try to use to measure soil mixing or bioturbation rates. Then introduce the case study where we look at soil mixing by earthworms with a published data set, and then how we use modeling to actually derive the mixing rate from the data set that we have there. On the top right, you can see which part of the presentation we are at, so hopefully you don't get lost in all the hopefully not too technical talk today. And this work is mainly based on a paper we have out in EGU Sphere, which is recently accepted in soil, so it should be out in a few weeks to months, I hope. As I've talked about soil mixing, we think about all the processes that actually transport material in soils up, down, or down and up. So the vertical transport of material in soils. They can have different drivers. For example, you have biotic drivers like soil fauna, earthworms, gophers, moles creating mole heaps, fallen trees also transport a lot of sediments in soils. But also abiotic drivers like freeze-thaw cycles or swelling-shrinking cycles, which all affect the way that soil material is redistributed in a soil profile. As well as, of course, humans have a big impact by, for example, by mixing by tillage operations. So these vertical transports in soils have a big impact on the current day soil functions. So you can imagine if you transport some mass of soil from the topsoil to the subsoil, the other way around. With that, you also transfer a lot of carbon, for example, or nutrients, which plants might depend on to grow. And if you have contaminants in the soil, this mixing process might also redistribute the contaminants or pollutants from the topsoil to the subsoil. And this process also have a big impact on the way that water flow is redistributed in soils, and also have an impact on the effect of soil erosion. So soil mixing process has a big impact on the current day soil function, so what we actually can do with the soil and what we can get out of it. But over the long time scales, they also have a big impact on the soil evolution or the development of soils. So you have three soil types: a chernozem, a cryosol, and a vertisoil, which are all developed mainly due to vertical mixing processes in soils. So both on the short term and on the long term, these mixing processes have big impact on how soils develop, what we can do with it, and what kind of properties they have. In this process, I will mainly focus on biotic mixing, on bioturbation, which means that the turbation, the mixing of the soil, is driven by biota, in this case, different types of soil animals. And we try to separate two different processes. One is mounding, and the other one is subsurface mixing. If you think about a mole digging around in the soil, creating a mole heap at the surface, you can consider this as a process of mounding. So the mole gathers material in the subsoil, in the subsurface, and transport this upwards towards the surface, creating a new layer on the top of the soil. The same would be the same for anthills, for example, or for termite constructions. So this would be like a transport from the subsoil towards the topsoil as a mixing process. On the other side, you can think about subsurface mixing, which is more like a diffusive process. So instead of transporting material from the subsoil to the topsoil, you have exchange between all the different layers in the subsoil as well. So you can think about a worm digging through a soil, going from a certain depth towards a deeper depth and up and down again. So instead of going towards the surface and depositing its soil material there, it just mixes up different parts of the soil layers. So often when you have a certain mixing animal, certain mixing organism in the soil, they often show both a combination of mounding, so they can transport some material to the surface, but they also have a big component of subsurface mixing, so they also transport material below the surface, you could say. And depending on the organisms and the way they behave in the soil, they either prefer more mounding transport over more subsurface mixing transport, or the other way around. So these concepts, this mounting and subsurface mixing, are based mainly on field observation. So if we look at the soil, we can see how the soil animals behave. We can see where they, if they create heaps on the surface, if they live mainly in the subsoil. So we have a bit of an understanding about their burrowing behavior based on what we can find in the field. The problem only is that we don't know exactly what these animals do. So do they prefer more mounding or prefer more subsurface mixing? What are the rates of these processes? So how much material do you actually transport as an effect of the bioturbation? And all these things are important to know if you think about soil function and soil evolution, because if you know the rates of soil transport, you can link this also to the rates of nutrient transport or carbon transport in soils. So understanding these mixing rates, these bioturbation rates, could really help us to better understand how soils function in natural environment and how we can benefit from that, or maybe use it also for more sustainable soil management. So we don't really know exactly what these animals do. We actually miss some, we don't have a lot of tools to measure these rates. So actually what's happening in the soil, how can we measure this over short-term, but also over long-term timescales? And we also need some simulation tools to simulate this process to understand how these soil fluxes due to bioturbation affect the soil properties and also the soil functions that come with these properties as well. For this process, I will start first with explaining luminescence, which is a tool for tracing bioturbation in soils, and then introduce the case study, and then show how we can use modeling to get the most out of the data that we have. So luminescence, or often also mentioned OSL, optically stimulated luminescence, is a property of mineral grains in soils that can be used to determine how long they have been buried below the surface. So these quartz or feldspar minerals, different types of soil minerals, act as dosimeters, so similar to radiation badges in hospital, where they capture radiation coming from the surroundings into their crystal structure. So this background radiation could simply be due to cosmic radiation coming from outside of Earth, but also due to the natural decay of radioactive elements in soils. So there's very low amounts of radiation, but this often occurs everywhere. This occurs everywhere in nature, and these sediments capture part of this radiation, store that as a sort of luminescent signal in their crystals. When the signal is exposed to daylight, so when it reaches the surface, you could say, then the signal gets reset. So the luminescent signal is lost when it's exposed to daylight, these grains. When they get rebirthed again, the system accumulates depending on the environmental radiation. So when you know the luminescent signal of a grain, you know the dose rate, so the incoming radiation from the surroundings, you can actually calculate the age of these grains if you divide these properties by each other. So here's an example. This would be like a time on the x-axis and the luminescent signal on the y-axis. A certain grain has a certain amount of luminescent signal due to the background radiation, which is this nice triangle here. When it gets exposed to the surface, for example, due to erosion or deposition or transport, signal gets reset. And the sediments get buried again, signal builds up, might get reset due to new exposure, builds up again, might get reset and builds up again. At this point, we can measure the luminescent signal of the grain and the background radiation, the dose rate, and then we can determine how long this grain has been buried below the surface. The luminescence is a light-sensitive proxy for the burial time of soil particles. We can determine how long they have been buried below the surface depending on their luminescence properties. So when we measure this property in a single soil mineral grain, we can determine the last exposure to daylight of this grain. So when all the grains have been exposed at the surface at the same time, for example, if you have like a dust cloud, all these grains are exposed to daylight during their transport, and when they are deposited again, they all carry a very similar luminescent signal, which creates a very narrow distribution of these measurements, which you can see here at the top. So a well-bleached sample means that all the grains are exposed to daylight at the same time. When you start to mix these grains, which you see at the bottom here, some of these well-bleached grains get exposed at the surface due to the transport and reburial. And therefore, these grains get a younger luminescent signal because they have been exposed at a later stage at the surface. So when you have mixing in soils, you also get a wider distribution of the luminescent signal, or also the ages corresponding to these signals, depending on the mixing that you have. So we applied this concept that you have mixing affecting the luminescence signal to try to determine the type of bioturbation that could occur in the soil. So when you think about mounding, so the transport of material from the subsource towards the surface, they expect that a lot of grains, a lot of soil material is exposed at the surface, exposed to the daylight, meaning you have a lot of bleaching, a lot of resetting of the luminescence signal. So all the grains would be would have a very similar luminescence signal in this case. So in this case, you have a very narrow DE distribution with maybe some other outliers depending on the rate of the bleaching, because this process exposes a lot of grains to the surface. For the subsurface mixes is the other way around, because then you have much less exposure to the surface, because you have much more subsurface transport and much less transport towards the surface and back into the soil. So you have much less bleaching due to bioturbation for these grains, where you end up with a much wider luminescent signal distribution, age distribution as well. But these two processes both have a different effect on the way that grains are transported into the soils, and we can use the luminescent signal of these grains as a way to trace what happened to these grains and what type of process was responsible for their transport. So we use this for a case study about earthworm bioturbation. This is a published study from 2023, where they dated a Chernism, so a black soil from central Germany, and where they look at the bioturbation of the soils due to anessic earthworms. Anessic earthworms are worms that mainly live subsurface, but also transport towards the surface and back down again. So they both do subsurface mixing and mounding, but we don't know exactly with what ratio they do this. So the black soils are very fertile in terms of their soil properties. You find them a lot in Ukraine and Russia, and where we sampled them, where they were sampled here in Germany, it's more like the most western region where these occur. So they took a sample below a burial mound. So they have these black soils were buried below a burial mound, and they could determine that this burial occurred about 4,000 years ago. And these soils were deposited about 13,000 years ago. So we really have a clear time frame of when these mixing processes could have occurred. So after the burial, the mixing stops because the land surface gets elevated. And before this period, we don't have a lot of activity because there were no earthworms active in this landscape. So we took 6 luminescence samples from different depths in the soil. And we could use this to look at the age and depth patterns of this soil. So on the graph on the right, on the y-axis, see the depth below the surface. So 0 would be the surface up to 60 centimeters depth. And the x-axis has the age of the sample, so ranging from 3.8 thousand years the left line up to about 13.2 thousand years on the right side. And the statistics of these distributions can tell us a lot about what type of process could have occurred here. So as we saw before, with the mounding, you get narrow distributions. With subsurface mixing, you get wider distributions. So we try to use this information to deduce what type of process occurred here. So we look at 3 properties. We look at the mode, which is the thick black line, which is like the peak of the distribution, so the most common age of the sample, which could be the burial age of the bioturbation age, you could say. We have the dashed line, which is the interquartile range. This is a measure for the width of the distribution. So the higher the interquartile range, the wider the distribution is. And you have the solid black line here, which is the bioturbated fraction, which indicates how much grains in a certain sample have been bioturbated and how much have not been bioturbated. So the higher this fraction is, means that more grains have been exposed to the surface and reburied again. And the lower this rate is, means you have less exposure to the surface. These 3 properties you try to use to understand what's happening in these soils. So far we have some field insight from the study area. We have some experimental insight from the luminescence dating. What we then try to do is try to calculate reworking rates in the soils. So we can divide the depth of a sample, divided by the age of a sample. It would give some idea about the reworking rate of this soil. So how long it took for these grains, which are at a certain depth, to come from the surface to be transported downwards to the location where we sample them and could measure them. If we calculate this for all the different samples, we get reworking rates of 0.01 to 0.05 millimeters per year, which agrees with about 20 to 80 grams per square meter per year. So that would be like the bioturbation rate based on these luminescence samples. The problem now is that if you look at measured data, for example, here's a review from Wilkinson et al. From 2009. They have rates from 500 to 0.5 to 6.3 kilograms per square meter per year. So almost 2 orders of magnitude higher than the rate that we can derive from the luminescence profiles. So these numbers are based on earthworm ingestion rates, so they measure how much sediment earthworms eat and spit out again. Also measure the weight and the volume of surface mounds to determine how quick the mounding rate is. This means that the luminescence-based rates that we have do not really represent the actual total mixing process, but only the net replacement of bleach rates. So we can measure the time it took for a single grain to come from the surface towards a certain depth. But these data do not account for multiple cycles of bleaching and burial, which we also expect to occur. Also don't account for transport of non-bleach particles. You also have a lot of subsurface mixing, which doesn't affect the luminescence age, but only the location of these grains in the subsurface. So we know that much more is going on in the background than we actually can measure with luminescence. If we can try to use numerical modeling, so process modeling, to derive the meaningful rates from this luminescence data. So how to actually simulate soil processes? First, we have to represent the soil landscape in numbers and matrices. So we know that soils have horizons and layers and certain coordinates and dimensions. We have to digitalize this. We have to have a conceptual process understanding and try to translate it into equations. So we know the type of mixing, but we have to make it into an equation for this. Then run the simulation of soil development, and we can then compare the model simulations to experimental or measured data to see what's happening in the background. So for this, I used the soil landscape evolution model called Chronolorica, which we developed last year. And this model simulates soil evolution processes like bioturbation, but also different erosion processes, and couples these processes to the redistribution of geochronometers, where you can think about the luminescence particle that we talked about as well. So we simulate the mixing of digital soil material, and together with that, we also look at how the soil properties and the luminescence and the other age information changes with these processes. Skip this part. So what we did, we translated the soil landscape system into numbers and matrices. So it was a one-dimensional soil profile, only with a vertical dimension, with a certain amount of layers, with a certain thickness, with a certain amount of particles which were included. And we based the environmental setting on the case study that we have. So we used the same type of soil material, the same duration of bioturbation for this period, and the same mixing depth. With that, we tried to simulate what's happening in the soil. So we also have to make equations for the processes. So the bioturbation rate is a function of that, with the highest rate at the surface decreasing downwards. And then with mounding, we transport the bioturbated material to the surface of the soil. With subsurface mixing, we can simulate the subsurface exchange of these properties. And then for the luminescence agents, these grains are distributed over the entire profile, just like normal soil particles in the soil. And their age increases with 1 every simulation year. But if they're in the top layer, which is a few millimeters thick, then their age gets reset, similar as exposure to daylight as well. So what we want to find out is what is the actual total bioturbation rate and what is the contribution of mounding and subsurface mixing in this process. So we did a lot of simulations where we combined different bioturbation rates, different fractions of mounding, different fractions of subsurface mixing to find out which was the best model setting to reproduce the data that we have in the field. So we could simulate the similar profiles we see here for the measurement. We could try to simulate similar profiles for the simulations and then just compare them and determine which rate would provide the best results. And it would look something like this. So on the x-axis, you have the percentage of mounding. So on the left, it would be no mounding, only subsurface mixing. On the right would be only mounding and no subsurface mixing. And then the colors indicate the bioturbation rate. And these lines indicate the calibration error, so the difference between the model results and the field results. And the lower the error, the better your simulation is. So if you look at the lowest point here, you can see that the bioturbation rate could have been around 1.5 kilograms per square meter per year, with 10% mounding and 90% subsurface mixing. So these rates are much more similar than the ones that we find in literature as well. So in the right order of magnitude, and also what we expect in terms of earthworm activity, they show the same ratio between mounding and subsurface mixing as well. We then compare the depth profiles. So we have depth profiles for the experimental data in black and the simulated data in red. And then for the different parameters, so for the mode, which is the most likely age of the distribution, the interquartile range, which is the width of the distribution, and FBO, which is the bioturbated fraction. We said overall, the model shows a relatively good fit with the experimental data. Of course, there's some deviation between the two. For example, for the simulated mode of the distribution, we see some scatter. It's a bit older at the topsoil, a bit younger at the subsoil compared to the measurements. And there's some explanations for this, for example, due to uncertainties in the experimental data, the way the process are implemented in the model, and also the way we select different statistics and evaluate the model. But more information on this you could find in the paper, more about the details. So what's important is here that we could actually use numerical models to get more out of our luminescence data than what we expect is already in there. So the luminescence data can help to trace bioturbation processes in soils, but do not capture all the movement which is occurring in soils. And then we need the field experimental insights to have an understanding of what are the actual processes occurring there, and try to translate these into meaningful soil process models, so bioturbation or mixing models. With them, we can actually derive meaningful mixing rates from the luminescence data. So the order of magnitude is much more similar to what we expect based on reported values. But of course, there's always some point for improvement to improve the calibration of the model and to improve the parameterization as well to get better predictions of the bioturbation rates and processes. So the model that we use, the Chronologica, is also applicable to other mixing and transport processes as well. So not only limited to bioturbation, but we're also planning to use it for different types of transport in soils and landscapes as well. All right, I think I'm a bit over time, so I'll leave it at this point, and I thank you for your attention.
Thank you so much. We'll just start the screen. We have some time left for questions and answers from the audience or any other scientists who want to jump in.
Thank you both for your presentations. I have actually a very general question, I think, to you both. So I am not a modeler at all, but I do a lot of field studies, and so I always gather a lot of soil data. Say I want to use this data for either upscaling or for modeling of the processes in the soil. Do you think it's possible to actually like afterwards contact the modeler and say like, hey, can we use this data for that? Or do you think this will almost always lead to that I missed something important? So should we sit together beforehand to be able to collect the right data?
I think you could be possible to contact the modeler to simulate process if you have a bit of an understanding what it is and how that works. Especially when you're specialized in a certain field, you have a lot of detailed measurement, for example. So if I think about soil carbon, it's like carbon is one pool of material in the soil. If you think about soil carbon as a biogeochemist, it's a lot of different types of carbon, a lot of different properties as well. So it's easier to aggregate complex measurements towards more simple measurements to model than the other way around, of course. But what we often see is also a bit of an iterative process. So you have to measure something, you try to model it, and often there's a discrepancy. It might lead to new hypotheses or maybe to new sampling schemes for future projects as well. So often these things are not first one then the other, but they should go hand in hand to co-develop, you could say. Yeah.
Well, Julia, do you have anything to add to the question?
Yeah, I'm sorry for the noise, but I'm actually from the other side. So I'm not a soil scientist purely. And I'm more of an hydrologist and remote sensing and climate model and that kind of thing. And I just happened to cross paths with a soil scientist during my research. So he had the idea of these cameras, of this simulating this climate change on soil. And we were already working together, and he came to me and said, so can you use this to forecast something, or can we extend what I found in these 2 years of study somehow? So that was an interesting question from him. And at the same time, I was looking into how do I take my model to forecast these shifts. which we never know how to model. So we only have measurements by statistics, especially at least in Italy for us. The organic carbon measurement are random. They're based on existing surveys. There's no real field data specifically. So the only way we have to see how it changed is to rely on 2012 data and 2021 data. So for us, that would be a 0.003% change. With this study, actually, what they showed was about 1%, which is a lot. Our soils are about 2% rich in organic carbon, so they're very poor already. So it wasn't planned to use that in a model. It just happened that we worked together on something, and brainstorming of idea, we thought that maybe something can come out of it. So of course, if you plan everything from zero, it's easier to get everything right. It's not easy. It's never easy, but at least you get some data that might work better than others. But at the same time, it does happen that you can find matching patterns and matching data that work for different fields, different aspects of the same problem.
Sure. So some pliability or flexibility, I think, as you try and work towards a question is needed. I think that was also thinking about your presentation, Julia, where you mentioned collaboration with field site owners, farmers, etc. as well. How important do you think that is to kind of building the understanding of the research area as well? Like, are they deeply involved, do you think, or?
So these ones are involved because we put out a call on people that would like to participate. So they are people that saw some interest, but in my experience when talking to stakeholders, if I show a lot of plots and data, actually models, pure models, it's very hard to get them to feel that that's happening, because it's a model. Okay, it could change. We know it's going to be in 100 years. Something might happen. A meteorite can happen, and nobody. But then, when you go in the field and you spend the summer picking up fruits and cleaning the dirt and digging the ground and doing all of that, and they see you there, and then at the end of the season when they get their crops out with the machinery and everything, and you're in your small pilot plot doing the same by hand, and then you show them the results, then it's, oh, so okay, so it's not a model. It could happen, very likely it happened here in your land, in front of your face, with your seeds, with your plants, with your everything. So it gets the message across easily, at least more easily than a purely scientific paper, which I also do, and nobody reads it from them.
So I guess that's actually more of an impact question, isn't it? How do you make sure your research has impact? It means probably some public engagement, some science communication involved in research as well. Beatrice, you just popped up on my screen. Do you want to ask a question, or is that a...
I was just hearing about Julia, and also how to let also people be involved into this kind of reality. Models are okay, actually, but real results sometimes are more efficient to communicate also to other people. And I totally agree with that, actually.
We do have a question in the Q&A box. Is chronolorica capable to track surface sea burial? That is not within my capability, I think.
Yeah, I've seen this as well. Yeah, so the stuff that I talked about with chronolorica right now is only simulating like a vertical soil profile. But the models actually developed to simulate interaction between landscape scale process like erosion deposition and the soil forming process in interaction. So models indeed capable to simulate the carbon cycling and how that relates to burial, for example, due to colluviation or some other erosion deposition process. And so it would be possible, but it depends a bit on indeed the setting that you have, the time scales of interest to see if the model is suitable, or you might need a different, more detailed or maybe less detailed model as well.
I think that's kind of most questions we have. Sigrid, sorry, you said you mentioned one more question.
Yeah, this is a bit also about the bioluminescence, the OSL data. So I was wondering how big these samples are, because this is related to the fact that what really would appeal to me for models is that I would be able to get a better representation of what's happening in the soil, because I look mostly at chemical data, and then often I take a tiny sample and I use it to determine, for example, the carbon content or whatever. But these are such small samples in such a diverse space, kind of. And I'm wondering, how did you deal with this with the OSL data? Because I can imagine you could run into these similar problems.
Yeah, so a sample is usually a PVC tube of maybe 4 or 5 centimeters diameter, which you push into soil horizontally. So the sample would be representative for a layer of 5 centimeters, for example. You could make it smaller, but then you need maybe a wider sample to get enough material to measure as well. But I think the challenge mainly here is also the resolution of the data, but also the reliability of the data. So if you do OSL sampling, you often get a distribution of ages. Also, if it should be completely homogeneous, you always get some scattering there due to natural variation in the minerals that you measure, some natural variation in the environmental background radiation. So the temporal resolution of the methods is not always matching with. So it would be like maybe decades upwards in terms of temporal resolution, which might not match with more recent dynamics, which you can measure on a daily to a seasonal scale. So luminescence, I would say, is more for the longer term processes instead of the recent dynamics that you have.
Thank you. So actually, we're very quickly running out of time as well. I don't think there's any last questions to ask. But with that, I'll close. We had 2 good presentations, I think, from different directions, relating soil sciences, well, field studies to modeling. So I want to thank both our speakers for the people attending today, and wishing you a happy World Soil Sciences Day.